Hello, in this video I'm going to solve question 6, Problems Set 1, Lecture 2, Lectures in Elementary Number Theory. Show that for any natural number n greater than 1, between n squared and n plus 1 squared, one can find three distinct natural numbers a, b, and c, such that a squared plus b squared is divisible by c. Pause the video at this point and give it a try. Okay, now let us solve this problem. Of course, the way that I present it first, I will solve the problem, but it seems weird. How could I come up with this solution? Then I tried to explain how I did it, but then of course I have to use a little bit of modular arithmetic to motivate you how I was able to solve the problem in the first place. So the problem is I want to find these distinct natural numbers a and b and c between n squared and n plus 1 squared if n is a natural number greater than 1, so that a squared plus b squared is divisible by c. Okay, the first thing that I do, n squared is just n squared, but n plus 1 squared can be written as n squared plus 2n plus 1. Okay. The numbers between them are the n squared plus 1, the next one is n squared plus 2, and then this list can continue until you hit n squared plus n plus 1, for example, and then this list can continue n squared plus n plus 2, and then of course you can continue this list until you reach n squared plus 2n plus 1. Okay. Sorry, I have to stop before that, so let me clean this until this one. So these are the numbers, all natural numbers between these two natural numbers that you can see here. Okay, I will pick this one and give the role of a to this and give the role of b to this, and I want to pick this one and give the role of c to this, and I'm claiming that always a squared plus b squared is divisible by c itself. So let us do that. So n squared plus 2 to power 2 plus n squared plus n plus 1 to the power of 2. So let us simplify this. The first one squared n to the fourth plus 2 times the first one times the second one is 4n squared, and then I have plus 4, and then I expand the second one, the first one squared plus the second one squared plus the third one squared plus 2 times the first one times the second one plus 2 times the first one times the third one and plus 2 times the second one times the third one. And let me simplify that. So here I have n to the fourth and n to the fourth, so the answer becomes 2n to the fourth. And then for n cubed I have only one single term, so 2n cubed. And then what about the n squared terms? This is one of them, this is another one, so far 5, and this is another one, 7. So this becomes plus 7n squared. And then I have only one single term involving the first degree term, so it is 2n. And for the numbers I have 4 and 1, which is 5. Okay, but now my goal is to factorize this expression and show that this expression, regardless of what value of n I have chosen, it is divisible by n squared plus 1. Okay, so for example here you can use long division, but let us factorize it here. So if you do the long division method to divide this polynomial by n squared plus 1 and confirm that the remainder is 0, you are done. So you have shown that this expression is divisible by n squared plus 1. Okay, but let us try to factorize it. To factorize this, here it's not very hard, so I would write 2n to the power of 4 plus 2n to the power of 3. Instead of 7n squared, I would write 2n squared plus 5n squared, so I break it into two parts, and then I have plus 2n plus 5. Okay, so now what I will do, I will group them. So between these two, I can factor 2n squared out between these two. So let me change my color. Between these two, I can factor a 2n out, and finally between these two, I can factor a 5 out. So that grouping is actually very effective here. So 2n squared I pull out, n squared plus 1 is left. Between the blue groups, I factor a 2n out, n squared plus 1 is left, and between the green group, I will factor a 5 out, it is n squared plus 1, and then you see that a factor of n squared plus 1 appears in all of them, so I can factor it out, so it becomes n squared plus 1, 2n squared plus 2n plus 5, and we are done. So I was able to show that if I pick this number and this number from the list of all natural numbers strictly between n squared and n squared plus 2n plus 1, then the second number in the list and this number, the nth number in the list, squared added becomes a number which is divisible by this one. So yes, I can give the role of A to this, I can give the role of B to this, and then I can give the role of C to this. So in principle, the problem here is finished. Okay, but how can I, because if you want to really do a trial and error to see which one of these numbers in the list fit with A, B, and C, that would be a little bit hard. So let me give you the motivation how to do it if you know a little bit of modular arithmetic, because according to my lectures, I haven't covered modular arithmetic yet. Okay, to do that, let me take a special case. For example, I don't know, let us take, this is just a scratch paper work, so let me just change my color. So here, n equals to 4, for example. So what are the numbers in my list? So n squared becomes 16, n squared becomes 16, and n plus 1 squared becomes 25, and the set of natural numbers is strictly between 16 and 25 are 17 and 18, 19, 20, 21, 22, 23, and 24. Okay, so but one thing is important to note. This number is already in the form of n squared plus 1, yes, where n is 4. But now let us consider module 17. Okay, so 18 in module 17 is just simply 1. 19 in module 17 is simply 2. Okay, and then this is 3, this is 4, this is 5, and this is 6, and finally this is 7. Okay, so be careful. What I want to do, I want to pick up from these numbers two numbers so that when I square them and add them, it becomes divisible by 17. Okay, and it is possible, you know, that it is important to see that because this number is in the form of n squared plus 1, and this one is already your 1, so you just need to look for your n whose squared plus 1 becomes 17, which means it is divisible by 17. Okay, and then of course, what was 17? 17 was 4 to the power of 2 plus 1. So it means that I have to pick this 21. Okay, 21 and 18 are my numbers, because if I raise 18 to power 2 and 21 to power 2 and I want to simplify it in module 17, the first one is 1 to the power of 2, the second one is 4 to power 2, but that is the way that exactly I found 17. 17 was 4 squared plus 1. So this becomes 17, and 17 module 17 itself is 0, so it is divisible by 0. If that one example is enough for you to detect a pattern, you just do it, or otherwise you give another example to understand the pattern, okay? So definitely it becomes clear that the numbers are involved in this kind of argument is n squared plus 1 itself, which is going to play the role of C, and this one, which is n squared plus 2, and this one, of course, this is very simple to see. This is nothing except n squared plus n plus 1. If you are not convinced with one example, you can have another example. Looking at those two examples, you can immediately convince yourself that is indeed the case. So n squared plus n plus 1 in this case is 16 plus 4 plus 1, which is 21. Okay, so by this example and having this in mind, you can at least come up with a guess, an educated guess, for the numbers that are supposedly play the roles of A, B, and C. And when you have them, then the proof becomes natural. So the rest of it is just simple algebra and algebraic manipulations. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.